Assalamu alaikum warahmatullahi ta'ala wa barakatuh. Bismillahir Rahmanir Rahim. Ladies and gentlemen, let's continue our computational fluid dynamics video CFD. In this video, we're going to talk about a very interesting topic. We're going to investigate the cooling of a PV panel using liquid. Okay, in one of my previous videos, we investigated the cooling effect of the air on a PV, but it was by one-way data transfer. I just simulated the PV panel in Ansys steady-state thermal, and after solving the fluid domain, which was air, in Ansys Fluent, I imported the results into Ansys steady-state thermal and to investigate the cooling effect. You can check out that video on my playlist. Okay, and also you can watch the Ansys system coupling one-way data transfer on YouTube. It is another video uploaded by Ansys itself. It shows the using one-way coupling between Ansys steady-state thermal and Ansys Fluent. Okay, today we're going to talk about the two-way data transfer. If the effect of the PV panel on the fluid domain is mandatory or it is significant, you will use two-way data transfer. So we have here modeling a solution of a spiral type hybrid photovoltaic thermal water collector using Ansys. Here we want to investigate the effect of adding inlet cold water to the PV panel, and then what is the effect of this panel, or especially the temperature on the water. Okay, in the previous video we did not care about the effect of the panel on the air, but today we have to investigate the effect of this fluid on the PV and the effect of the PV on this fluid domain to get the outlet hot water temperature. Okay, so let's get started. We have similar or approximately, let's see the geometry. We have, it is not as the same as this geometry. We have different dimensions of the PV. So in XY, just import. We're gonna add the PV as add material. Okay, and it's just one layer. We'll take the silicon properties or the PV cell properties. We're gonna ignore the other list for just simplicity for this tutorial, for this simulation. Later we're gonna see how to add the other layers. Now the cooling fluid is that frozen. Okay, notice no gap between them. You must find no gap, okay, for the inner face. No gap, just tangent. Okay, if there is any gaps, you will not be able to find heat transfer. And here is the cooling channel. It's gonna be liquid. We're gonna ignore the thickness of the copper. You know, it's a copper material, and the fluid or the liquid, the water flows inside of it, but we're gonna only simulate the liquid because the thickness of the copper is very small. Okay, so here is fluid and the panel is gonna be solid. Okay, let's close. So now I'm not gonna use Fluent at first. I'm gonna just share the geometry. Okay, and before opening the mesh, we have here the PV cell, and we have here the isotropic thermal conductivity. Let's see the properties. It's 148 watts per meter Kelvin. Okay, and here is the density. If you do not find what you want here, just open the engineering data sources and check all this. Okay, because I did not find the density now, it's here. Okay, so where is PV? Okay, yeah, because I defined it before. Now we have the density loaded 2330 kilogram per cubic meter, and specific heat 677 joule per kilogram Kelvin. Okay, I'm not sure if CP or CV, just put the value that you have. Okay, now let's close this. After that, we chart the geometry. Now we're gonna investigate the PV with no cooling at first. So open the meshing. Okay, we have here, we're gonna investigate 900 heat flux to see the temperature. Okay, so this is the model. Yeah. Okay, first we have to suppress the liquid domain because it can't be here. Here, solids already accepted. Before doing anything, you must select the material, PV cell. After that, you must also calculate the suitable mesh size, but for this tutorial, for simplicity or for saving time, just gonna use the fine here automatically. Okay, but you must exactly calculate the suitable element size and carry out a mesh dependence study. Okay, and here the initial temperature, we're gonna make it 300.15. Okay, just update the mesh right now. So we have here a steady state heat transfer panel without cooling for different heat flux. Okay, natural convection is 10 watt per square meter Kelvin, and full temperatures and found out. Okay, we're gonna do this right now. So here is the mesh. Okay, and the initial temperature, analysis setting. I'm gonna leave everything like this. Just insert heat flux, which is gonna represent the solar flux. Okay, watt per square meter, 900. You can change the units from here. Okay, and here, so the 900. And 10 for the convection for this side and for that side. Both are facing, no, sorry. Here is insert convection. Yes, film coefficient is gonna be 10. 10. Make sure that the units are okay. We have the same temperature for the ambient. Okay, now we wanna get the temperature with no cooling. There is no cooling channels here. So let's see what is gonna happen. Just click solve. You should follow the same steps if you wanna validate the paper. I mean the researchers follow the specific procedure. If you wanna validate their work, you should or you must follow the same procedure with the same parameter conditions on the same dimensions. Otherwise, you will not be able to exactly get their results. Especially the mesh dependency study and the factors I mentioned. Okay. So, gentlemen, as you can see, it is not the same. Okay, I did this to show you what we have to do right now is if you open the convection, I just selected one face and here and the other face. Okay, now we're gonna select all the faces, the 6 faces under natural convection. This is more realistic or more logical. Okay, let's solve it again. Okay, let's see the temperature. So as you can see, we get the same distribution. As I have just said, if you do not exactly follow the way they followed, you will never be able to get the same results. And I have just proven this to you. I just selected 2 faces, but it did not work. It did not actually get the same distribution. Okay? So we have here 344.9 as minimum, 345.15 as maximum. This is with no cooling or without cooling. Okay? Okay, this is finished right now. This is the first step. Now we're gonna investigate the cooling effect. Okay? Of course, you're gonna duplicate your projects here, but here I'm gonna just reset everything to take the effect of the cooling. Let's do it again. Now suppose that we're gonna investigate the cooling effect. So what we should do is as follows. Just open your model. Okay, first of all, the geometry. Suppress this. PV cell. Initial temperature. Analysis setting. Okay. Insert convection or influx. Only the front face. 900. Okay, this is pretty good. Then the convection, all the faces, 6 faces with 10 with the same ambient temperature. Okay, and for the mesh sizing, fine. And one more tip here for fluid solid interface, it is gonna be the back surface. This is the surface that is gonna receive the heat from the cooling liquid, okay, and then will transfer the temperature of this surface to the cooling liquid. So this is the fluid solid interface. After that, just insert, we need the temperature. Also, if you wanna exactly get the temperature at a specific location, you can create the coordinates. If you have a thermocouple at specific location, create coordinate system. Yes, this, and then here is global coordinates, and just put the origin x, y, and z, and then to locate the point, exactly the point. Where is the point? Or here is, for example, it's gonna be 0, and here is something like this. For example, something like this, exactly on the surface. Okay, you have to know exactly where, and here is y, something like this. Of course, I'm just showing you what to do, but of course you have to know how to locate the point on the surface based on the y and the thickness of this panel. Okay, after that you insert probe temperature, and then coordinate system, and then coordinate system, or the point at the specific point you got here. You can rename this point 1. Temperature probe is gonna be on point 1. Okay, so I'm not gonna do this because it is not the correct location. I showed that in detail in my video about cooling the PV using grips. So you have to check this out for more accurate inputs. Okay, now we're done here, so let's close. Okay, after that you update this. So take some time. Yes, after that just update also the setup. We're not gonna run this because we will wait until we define everything in Fluent, and then we were gonna do the coupling to be solved at the same time. Now we have this mesh. Open the mesh. So after opening mesh, must here suppress the panel. Now we have only the liquid domain. Okay, it's gonna fluid, and then we have the mesh. Again, gentlemen, you must carry out a specific procedure to get the mesh. And for this tutorial, for simplicity, I'm gonna use the default. Let's update it. Of course, in the paper they used As you can see, the nodes and elements are, as you can see, 1,255,938. Of course, I cannot generate this amount and run it on my computer. If you wanna get their results, you must use something like this, okay, following the same procedure. Okay, of course we have here this statistics. I have 411,916. This is very huge for this tutorial, so I'm gonna use another size just for simplicity. Okay, this is pretty small. Okay, let's put this. Okay, just like this. Okay, I just update it. It's a pretty coarse mesh to make the solution faster, or the solution simulation faster. Okay, I do not now expect to get the same results, of course, because of using a coarse mesh. Okay, now we have to give the name selection. Name selection here is the cooling fluid. Okay, and we have an inlet and an outlet. So suppose that this is the inlet. This is the inlet, this phase, and the outlet. Okay, also depends on the experiment itself. And now we have here, this is the, here are the faces that will be in a direct contact with the PV panel. Okay, so we're gonna select these faces as a fluid solid interface. Okay, these are the faces. By the way, now here it's all of them are selected just because we did not split the pipes into bottom and front and back. So just for simplicity, you can do something like this. But if you only wanna select these faces or the direct contact with the PV, you have to split the pipe itself to be able to select the front face without selecting the back. Okay, but just for simplicity and to save the time, I'm gonna use this as FSI, fluid solid interface. So now we have the cooling fluid and the inlet, outlet, and the FSI, and this is it. Now we update the mesh to start Fluent. By the way, the maximum skewness of the mesh must not exceed 0.98. You have to open the mesh again and see the quality, the skewness. So the maximum skewness must not exceed 0.98. In this case, we did not exceed that value. Again, I'm gonna show you. So here is maximum 0.55. Okay, so this gives convergence. For the setup, Just reset this, and based upon your the number of your threads, you can use the Perl and with double precision to increase the accuracy of the solution. So I have here 4 threads can you work together. I'm just gonna use 3 or 2 to make the solution faster. Let's open it. So here, based on this, we have here the diameter. I think that we have the same diameter, and so we have here the hydraulic diameter and the properties. It's gonna be a steady state simulation, not present. If you have the significant effect of the gravity, you have to put its value, but now we're not gonna take this into consideration. Okay, if it is air or something that the gravity plays a good role, you have to use the gravity. Okay, energy of course on for the temperature, and we're gonna use K epsilon model. Here standard model, so the value of turbulence is 65%. That's K epsilon, and you have to study these things. By the way, enhanced wall treatment or the standard, you have to get this from the Ansys theory guide. Okay, after that the material, water liquid, okay, let's copy, close, and here are the properties, and then the cell zone, make it water, and just like okay. And for boundary conditions, we have here the inlet is gonna be mass flow inlet, rho Q. I'm gonna simulate at 66 liter per hour. 66 liter per hour. Liter per hour. Okay, cubic meter per second. This value, multiply this value by the density of the water, 0.00833. Okay, it's gonna be 0.018 kilogram per second, and it's gonna be normal to the boundary 5% with the hydraulic diameter where is the hydraulic diameter? $15.275. Okay. Alright, no step condition, but for the walls, of course, it's the default, and where the outlet is 0 gauge. and the same hydraulic diameter. By the way, the thermal will be 315. Point 15. 300.15. Now for the fluid solid interface, it's a wall, but you have to put it here is via system coupling to receive the information from Ansys steady state thermal. Now we're done here, nothing more. The methods, depending on the things we have here to make it coupled, and based on the mesh you get the correct things here. You have to study carefully these things, but for this tutorial, because I do not have a very good mesh, I'm gonna leave everything like this. Also for the monitors now, or the residuals, you have to increase the zeros here to make the solution converged like this. Okay, but you have to increase it because of getting more accurate data. Okay, now I'm gonna put a monitor, surface monitor, because I need to monitor the average temperature of the outlet. Remember that we wanna get the outlet temperature, water collector outlet temperature. I have to get it as an average. So you have selected the outlet and report file, report plot, but do not print it to console because I'm not gonna open Fluent during the solution. Okay, so this is the outlet and your area with it average. Do not print it to console, just to click OK. And so let's initialize. Okay, now this converged because this is the lowest value. If this is the lowest value, okay, you may get a warning here, so you have to create another mesh size and so on. You must find this in photo view. Okay, now the calculation, it's gonna be 200, but it's gonna be overridden by the coupling. Just save. Okay, do not close before making sure that this is okay. Just close. So now it is the time of coupling, system coupling, two-way data transfer. Just get the setup here and the setup here. Update. Okay. Just wait. And then we're gonna update the setup of Fluent. And then the setup, update. That doesn't take so much time because of the low elements count. More information. So update setup. And okay, now here we go. Open the setup, yes. Simply the analysis setting is not gonna be changed. The iterations, you can get all the information you need from the other sources. Increasing the iterations will increase the time of computations. Okay, now click on this and this. Just create data transfer between the fluid solid interface in mechanical and the FSI in Fluent. Now it's okay, everything is okay. As you can see here, data transfer, steady thermal to fluid solid interface, here at the temperature, and here to fluid flow. And this, the same here from fluid flow FSI to the steady state thermal. And here something, and here the convection, and here the convection coefficient, here the convection represent these things, as you can see, and so on. Okay, just click update. So no warnings or errors. It will not take it will not take time because the low mesh count. Okay, and the simulation is starting, getting information about the systems. Be sure before opening the system coupling that the project of Fluent has a specific name which is different from the Ansys steady state thermal name. And we have here this case because we have fluid flow Fluent and then steady state thermal. To be able to distinguish between them. So here is the first iteration. Okay, as you can see, the solution starts. That gives you assisted thermal conversion, not yet converged, and then fluid flow. You can enhance these things, of course, by higher quality mesh and second order discretization, like I said. So as you can see, gentlemen, it takes some time, even if I have low mesh count. Truly, it's a time consumption procedure, as you can see. So what if you use over than 1 million elements? That really needs a very, very strong CPU. I'm not posting the video just to tell you how complex this system is. Even if I use a low quality mesh, it takes some time. So it's gonna stop at 5. Okay, 3. So if you do not have a strong CPU and you cannot generate the mesh requirements like the paper, of course, I don't think that you will be able to validate the results exactly like the paper, because the mesh size is one of the main factors that affect the solution numerically. So we have here fluid flow, fluent, data transfer change, and steady state thermal, and the third one. 4, and then one more iteration. Okay, ladies and gentlemen, here the system coupling service shut down. System coupling run completed successfully. This is pretty good with no errors. Now we can get the solution. So let's update the results. Okay, to see the effect of cooling. You see here, this is without cooling. I expect lower temperatures, okay, even if I do not get the same distribution here because of using a very coarse mesh. Okay, it's okay. And let's see, let's open results. So we have here the PV. Okay, let's see. So the temperature is 340 as maximum and 304.7 as minimum, which is pretty good for this mesh accuracy. Okay, there is no simulation, just yeah, there is a simulation. Okay, as you can see, this is the steady state solution. This is pretty good. Okay. Okay, anyway, this is what we got after the cooling effect. Now let's see what happened. So here is Fluent and the contours. So let's see all this. So here is 300 to 340, and this is the distribution using the coarse mesh. Okay, as you can see, this is the effect of the PV panel that is receiving solar flux on the water Okay, that's why the two-way data transfer is mandatory at this case. So the last thing now here is the monitor. You will find the monitor here in the location directory Excel. This is the temperature of the outlet, and just copy it, and then this is the time history, or I'm sorry, there's no time here. This is the value of the temperature. Control A, just insert this. You will find here the temperature. This is the value. You get the final value of it. Okay. This is because this is not a transient simulation. Just this is the final result. Of course, it is not like this result. Why? Because again, the mesh is not like this simulation. It should be water collector outlet temperature is gonna be 306 or 307, but here it is higher because not using the same quality of mesh. Okay, but it's okay. So now, gentlemen, suppose that we're gonna add some layers for the PV. For the simplicity here, I'm gonna just add the glass, and you, if you are interested, you can add the other things. I covered these things in my previous video, especially the solar tracing and the related videos. I'm gonna add the glass 3 mm. After here, we have, after this, I have here, okay. So I'm gonna extrude this just 3 mm, apply as add frozen. Okay, okay, just 3 mm to express, to present the glass. Okay, so we have here, what we got is this layer glass and the other layer. Okay, this is glass, and then the PV cell itself, the PV cell. Okay. Yes. Now this glass is gonna be solid, and there's fluid, and it is solid. The same thing. Just refresh. Actually, the setup of Fluent is not gonna change. Why? Because it is the same cooling domain. Okay. We're gonna prepare Fluent and then leave it now. Open it and update. We have to suppress the glass. the glass must suppress it, and that's it. The same thing here, because no changes. The FSI is the same direct contact with the PV cell. Okay, everything is okay. Just gonna refresh the setup, open it, and we're gonna just initialize it again. Nothing changes. Of course, you can add the other layers. I'm just showing you quickly if you wanna add any layer. Okay, the same setup, the same thing. Just initialize it. Okay, and then file save. Now we're gonna investigate the PV panel after using the glass with no cooling, and then we're gonna see the effect of adding the cooling fluid. Okay, now it's okay. Just share the geometry. Yes. Engineering data. Okay. Get glass is thermal conductivity. Density. Solid glass is 3000. And after that, thermal conductivity. Thermal conductivity 1.8. Okay. After that, specific heat. Okay. Can use this. Gonna be the glass 500. Gram Kelvin. Okay. And thank you. And then we open the model. Refresh. Okay, starting the mesh. Okay. Once again, we're gonna suppress. So this is the glass, okay, it's suppressed. Here is the this is suppressed, okay, the panel, PV cell, and here is the glass, must be glass. Okay, just update the mesh. We're gonna use the same thing. With the same fluid solid interface, because the glass is added in front of the PV, not on the back of it. Okay, heat flux and units here, yes, and the convection, everything is okay here. This is the FS, okay, and here is the convection. But the convection, by the way, now we have 12 phases, and the heat flux is not gonna be the face we used before. No, it's gonna be the front face. Now it is the glass, so you must do this. It is the same things, they are the same things but different faces. So this is the face, yeah, that was gonna receive the heat flux, okay, and then here is the PV, the convection for the whole faces. Now we have 12 faces. Okay, these things really affect the solution. So close. Now I'm gonna start system coupling. Just update. Or I'm gonna solve it to see with no cooling, and then we're gonna use with cooling. Okay, just open it again and just click solve. Gentlemen, again here, the heat flux, this, okay, the convection, just to make sure we have this face and we have this face and this face. This is from this side, and after that we have these faces, okay, and then we have this side, we have these faces, okay, after that we have this side, we have this side, and this side. So this is the convection. So it's just 10 faces, gentlemen, not 12, because if you click on Control A or Control or everything, you're gonna choose also the interface between the glass and the PV, and of course the interface is not receiving any convection. It is very wrong to include it in the convection heat transfer. So now please, you have to select each face manually. Do not use Control A. Now we have only 10 phases. The 12 phases came from considering the interface between the glass and PV cell. We have here this interface, one phase for the PV and one phase for the glass. So we have two more phases, but you must exclude them. This is pretty important. Okay, now we hit flux only the front face of the glass, and this is okay. Now click solve. To see with no cooling. So 345 and 341. This is the effect of using the glass. So as you can see, this is the new distribution. This is pretty impressive. This is the effect of adding the glass. Let's take a snapshot to compare it with the cooling. Let's make it 1. And 2. Okay, just close. Okay, the solution, just reset the solution. Okay, system coupling. And setup, just update the setup. As you see, adding the system coupling really increases the complexity of these kind of simulations. And then the setup of Fluent, update. Nothing changed in the Fluent setup. We have the same FSI surface. It will transfer the data to the PV cell. The only difference here is the convection phases, 10 phases, because we added more 4 phases. We had 6 phases, and not considering the inner phases, which are 2 phases, so we got 10. And of course we changed the phase that receives the solar flux. These things are really you may not consider it, but it affects the solution. It makes your case not realistic. So update, and hopefully now we can run the coupling to see the effect. Again, fluid solid interface and FSI, create data transfer, and then hit update. Let's see. No warnings or errors. So here reaching 4. Now we're waiting for the last iteration. Really, it is like the tortoise. Really, it's a big deal to use the two-way data transfer. It's a big deal. It's not easy, and it requires stronger CPUs. Even if it is a simple case. And here we have 5. And system coupling service shut down, system coupling run completed successfully. Congratulations, and we're done. Now let's see the results. Okay, let's see. Update. Okay, open the results. We have this with no cooling. Now we're gonna see the cooling effect. So the temperature here is 340,304. As you can see, 345,341. This is with no cooling, with glass, and here is after. So as you can see, here is the distribution. Yes, this is the panel, and we got here 340 and 304. Okay, is this the effect of the adding the cooling channel? Okay, which is pretty good. And if you can see here, we have 2 layers. So this is the glass, and here is the PV. Okay. So we have this distribution, and it is the heat transfer by conduction occurred between both layers, as you can see. So this is pretty impressive. We succeeded in cooling this, and here let's go to Fluent to see what happened. So here is the graphic, or the graphics, temperature. Okay, here is the contour. Okay, nothing is quite has changed. Okay, before adding the PV, because the glass received the same amount of solar flux and transferred the heat to the PV cell, and then the PV cell transferred the results to this. Okay, so gentlemen, this is for this tutorial. Thank you very much. I hope this helps you. Actually, in this video we showed you the effect of cooling the PV by the liquid, and we have here the simple case with no glass, and then we added the glass and with no cooling. Thank you very much, and I hope this helps you. Wassalamu alaikum.